Okay. Today I promised you in my last video that I was going to do something on a CH4 report, the mining using this bladder tank idea in the mining of methane hydrate. But I want to tell you this type of this material that I'm working on right now is not what I want this channel to be about in the first place. I'm actually a lot more into prophecy, nation building, law and order. Want to talk more like Thomas Paine and Adam Smith, especially his morality. And in the end result, though, this bladder tanker or bladder tank technology, in Adam Smith, in honor of him, it's actually an open market to the world. I mean, this could appeal to anybody, anybody who has the capital expenditure required to develop a technology like this in the first place. In other words, like the Saudis, they have held on to a lot of money. You looking for jobs and stuff. I'm not saying that this idea is going to do anything, but it's a way of looking at, hey, what might be available. You can get in on the textile manufacturing. Anybody could get into this field. Having said that, I'm going to move on. I'm going to get on into this. Let's talk about, I want to talk about the world oil supply, okay? Technically, what we know of, both in what we're producing in the ocean and what we're producing on the land, these proven reserves that we're working on, this oil in this conventional pumping oil, we have less than 70 years of oil that's available in this ready pump. Now, when we throw in oil technology like shale oil, and we throw in the tar sands, we add another approximately 75 years of regular oil supply that we know of. Okay. The ocean, even though the bladder tanker idea is pretty neat and it could be used in some marginal fields, the problem with finding oil in the ocean is that the ocean is largely basaltic rock. In other words, for all intensive purposes, you might as well call it moon rock. There's just not anything living out there. It never has been enough of anything to really bring about any sizable oil deposits out there. I think basically what I'm saying is we pretty much have an idea that the deep ocean crude isn't going to be a major supplier of oil. And that may change a little bit. But anyway, we're looking at about 150 years that we will actually have oil from all sources. I want to talk about atomic power, and particularly fission power. Now, you all know we have uranium reactors and plutonium reactors. We have the uranium, like just your heavy water reactors, whatever. Plutonium is a type of reactor. What happens here with uranium, if we simply use uranium for nuclear power, our known reserves, at least anything we have any real sense of, would last about 1,000 years. It is imperative that we, in place of using these conventional heavy water reactors that use uranium, we have to develop and use breeder reactors to produce plutonium. We must use the uranium we have now in breeder reactors so we can produce plutonium. If we produce plutonium in this way, our atomic power could last between 5,000 and 7,000 years. Okay, now the big thing is we're still working on fusion power. I'm a big fan of everything going on in fusion power. We're still a little ways away from it. Hopefully, hopefully we will actually be able to achieve it. You know, there are some things that we may not be as possible as we really think. But anyway, I'm not gonna do anything with that topic anytime soon. Anyway, I would like to I would like to point out when we're talking about green energy, windmills, and I just make an example of something. If we were to use windmills to provide all of the electrical power of all the energy that we use in America, including electric cars and stuff, converting into electric cars, we would in our industrial processes, we would need between 2 and 4 million windmills for America alone. That's just a little, got to throw it in there for you. It's funny because that might actually, all those windmills gyroscopically spinning might actually affect the tilt of the earth. And then if the earth quits spinning, I don't know what we're going to do. Just kidding. All right. Now I want to get into something here, get a little more on topic of this paper and the methane hydrates out here. It's estimated that we have is somewhere as a minimum of 1,200 to 3,400 years worth of energy locked up in these methane hydrates if we can find a way to utilize it. We have more energy in the ocean's methane hydrates than we have all the fossil fuels on land combined, coal, gas, and oil combined. That's a big thing to look at. Now, okay, I'm going to get back on here. This is really funny. One thing here, if we can produce a lot of methane hydrate, we can leave fertilizer, oil for fertilizer, and other things like plastics to begin with. It'd be neat if we could make a transition. One of the things here, I want to talk about one thing here just about energy in general, because in reality, when you look at the amount of energy we use in the armaments industry, I'm talking about it takes energy to heat steel, to produce iron ore, to turn it into steel, to make tanks and ships and all this other stuff, just right off of the bat. All of this stuff is energy intensive. The reality of it is, by the time it's all done, said, and wrote, I'm going to say that at least half of all the energy we consume in the world is used to make weapons of war, to fight wars over it, I guess. It is mind numbing. And I'm beginning to see this methane hydrate production that I'm going to get into here. I'm seeing this more as a vision for capitalism here. Something, because here, one of the things here for me is, if you can produce this methane hydrate, what I'm getting at here is you need to quit buying energy from people who are using it against you, okay? You're just making a bunch of terrorists rich. The more we spend on Iran's oil, the more money they spend on nuclear bombs. And we're back to that problem here of uranium becoming plutonium and breeder reactors. See, there's that big secret again. For the record, plutonium out of a breeder reactor is a much easier process to turn it into a bomb than the uranium, processing uranium, enriching uranium. But in reality, it's not really energy that is the problem in the world today. We actually have quite a bit of energy, and it looks like we're going to do okay one way or the other. But we do have a problem emerging here in production of food and water. These are becoming some problems. The world has always had a problem with famine. That's nothing new. And you know, part of it is starting to sound a little bit like the one riding the brown horse when I start talking about food and famine and water resources and war just in general. But those are topics that I really like to talk about, but I'm not going to elaborate on here. I'm going to get back into this uh, program here that I want to talk about today. I'm going to, first off, I'm going to list a few takeaways. This whole idea, the whole idea of a bladder tanker and marginal oil fields, that's cool. That's a real good idea. It could be of use. Copilot seems to think that that might be a $1 trillion business. I don't know if it's worth developing it or not. The other big takeaway is that nodule mining, using the concept of using a hydraulic cargo tanker to lift nodules up. See, right now they want to turn that stuff into slurry and pump it. With a hydraulic bladder tanker like this, that gives you two ways. You can take stuff up and you can bring stuff back down in a controlled form. And it's really good if you can tap if you can tap a source of oil somewhere on the ocean floor, somewhere at a depth very close to that nodule region. See, run you a very low pressure hose to fill those balloons up. The idea that's so much better to use oil instead of trying to do it with like airbags and stuff like that, which are really not that good. And again, even with airbags now, you've got the problem of how to get the air down there. And if you're going to try to pump air in at 10,000 feet, you're going to be looking at 300 bar. Lots of luck. Oil, however, is different. As long as the oil source is down on the ocean floor, somewhere close to this, it makes that whole idea feasible. The other takeaway here was something here that AI had informed me on the coming off of on these oil wellheads on this ocean production here. You have, I guess, you have a lot of water, sand, natural gas, and oil. And one of the first things they do is they run all that stuff through a separator, and it separates it all out. Now, Copilot was telling me that having these bladder tanks down here now, keep in mind, if you're say at 6,000 feet, these bladder tanks are at a natural 183 bar. Okay, they're already very high pressure, simply because the ocean around them is the containment vessel, and it's not really the material that the bladder's made out of. As long as you can keep it, you can depressurize it a little bit, venting some of the gas off. But apparently, this is a big aid. This natural gas coming off of these wellheads, after it's separated, is very high in H2S, that's hydrogen sulfide. And it also has a high content of heavy metals, particularly like mercury. And for reasons that I don't really know, I have a pretty good idea. This is going to be a really dense gas. It will be very dense at these pressures. It might be a lot easier to clean and process before you move it on. So that was something about these collapsible bladder tanks, and they're tanks, not tankers. Those things, like the methane hydrate process, these things are not going to move. Those kind of tanks like that would simply sit at the bottom of the ocean floor and be processing natural gas, and perhaps actually separating all of that material without it ever being going anywhere. So I think that's a big takeaway. That was something that Copilot or AI informed me on. Now, when we get into what I'm going to do here with methane hydrate, I'm going to show you the use of these bladder tanks. They're not going to move, but they will provide the single biggest criterion for methane hydrate production, which is the concept of depressurization. We'll cover this here in just a minute. Okay, I'm going to move into something here I want to talk about for just a minute, especially markets. I mean, capitalism is all about markets. I'm going to tell you something that's really amazing because in America today, natural gas production of electricity by natural gas, I believe, is the leading method. I have a chart here, thing here. I'll put that up. I'm not looking at it right now, and it surpasses coal in electricity production. The other thing, when we flip over to Europe, we find that most of European electricity is still produced by coal, but natural gas has a pretty big share of the market out here. The one thing that I really like about natural gas, number one, natural gas is very low emission. It's mostly CO2 and water. And in this methane hydrate production process, I'm going to demonstrate where we can actually sequester CO2 and restabilizing these methane hydrate fields that we're going to be working in. I'll cover that later. However, you know, if we start really producing a lot of electricity with natural gas, it really starts to make electric cars much more attractive. Now, I'm going to point out to you here, I'm not an opponent of nuclear power. I like some of this SMRs, these small modular reactors. Those are pretty cool ideas, you know. However, I would like to point out that, you know, Einstein once said famously that he didn't think it was a good idea to boil water with atoms to produce electricity. And of course, we can look back at Chernobyl in 1985, which is biblically the wormwood of the time. And we can also look at Fukushima. I don't remember exactly. That was somewhere in the year 2000s. Part of the cost of nuclear power is cleaning those messes up too. See, we got to keep that kind of stuff in mind. So if we could actually go gas, the more gas we went, the better. The other thing, this concept I'm putting forth here is going to take the tech bros to the limits here. All right, we're going to be looking at technology that I will call AI robotic mining. The big part of this mining operation, which will be slurry mining, will be done by AI robotic equipment. We'll be talking about the concept here in just a minute. And so there's some big possibilities here for the development of technology. We can do this. I'm convinced of it. And now I'm going to go ahead and move into some of the base concepts here. One thing here about methane gas hydrate production here is the concept of depressurization, okay? And more specifically, a containable depressurization of the hydrates is this. Gas starts boiling out of the slurry. One of the easiest ways to aid that is to provide depressurization. Now, this is where the bladder tank itself becomes very valuable in this process. The overall depressurization of this tank can be governed by the difference in the depth at which methane hydrate is being produced in our mine versus the depth at which these balloons are positioned or moored. In this case, initially, I would propose that we would keep the floor, or at least the mine shaft itself, the opening of the mine shaft at 2,000 feet. Okay, at this point, we have a bar rate of 6129 or 61 atmospheres. Now, our decompression, these bladder tanks would be at a depth of 1,000 feet. They would be at 30 bar, or roughly 30 atmospheres. This would provide a drop of 46 atmospheres in a contained, and it would be a contained depressurization. This would be one of the reasons why I like starting at this is because at 2,000 feet, we actually are still at a point where we can actually have divers. They're very specialized, but people can actually dive to about 2,000 feet in special training in open ocean diving. See, your scuba or your just regular divers can go down to 1,000 feet, which is neat because initially we could have a certain human presence to kind of oversee things. Not that it would necessarily be that necessary, but it would also give us a region where we could develop things a whole lot easier to move things around. This entire system is going to be intended to be modular in that after it's worked in one mine, the major components of this can be can be taken apart and moved to another mine. Now, one of the things about methane hydrate that I found out too was methane hydrate, when you produce methane gas from methane hydrate, this stuff is actually extremely clean. It is very, very low in H2S, hydrogen sulfide, very small amount of it. And in addition to it, the heavy metals like mercury and stuff like that are very, very minuscule. There's very little of those materials trapped in the methane hydrate gas. It comes out what the industry calls nearly pipeline ready. Now, these bladder tanks, I've got an idea that these things, that 100,000 barrel size tank that I was talking about for oil, it's really nice because that equates out to about 500,000 cubic feet of gas. And again, depending on where those tanks, the depth at which those bladder tanks are positioned at will give you some degree of higher compression. In other words, if your tanks are at 3,000 feet, you're going to be at 91 atmospheres, in which case that gas is still fairly dense and still can be pipelined onto the shore. Once it gets into these bladder tanks, it'll eventually be drawn out and feed a shore pipe. Okay, now I'm going to cover this whole concept. One of the big things about methane hydrate production today is the cost of mining. Now I'm going to demonstrate to you through this process here of using these bladder tanks to depressurize methane hydrate quite literally on site. I want to emphasize something to you here. There's a lot of things to looking at the cost of mining and how to reduce it. As I look at methane hydrate, one of the first things that comes to my mind is all the Hamiltonian mechanics present here in phase changes. Okay, your physics of Hamiltonian mechanics right here for you. Now, I want you to understand this because every molecule of CH4 is like a compressed air tank, okay? When you rupture that air tank, that gas molecule expands 160 times, okay? You keep that in mind. And essentially, in the mining process, you actually have access to a very high volume of high pressure compressed gas to begin with. In the whole concept of mining methane hydrate, I like to point out that you can engineer this to be a gusher all the time. In other words, as you process this methane hydrate and it depressurizes, you can use it. It's like a gusher all the time. The pressure never dries up. You can always control the pressure by where you're doing your methane hydrate. Now, I want to also point out that in your slurry pipes, especially the ones that are heading to your risers or part of your risers on the way to the depressurization, the contained depressurization that the bladder tanks are going to provide, you can have what I would call just an adiabatic generator. In other words, if you're going from some kind of a pressure at 76 atmospheres and you're going to 30 atmospheres, that's a pretty big drop. You could actually use that to drive a slurry, to drive a generator. You could put a turbine generator in that stream and actually generate power, on-site power for your mining operations, whatever you'd want to do with it. It's kind of a neat idea. Then, of course, the deeper you go, the better this process becomes, but it's something to keep in mind. Now, okay, I'm going to talk a little bit here about the main, what you might call, I guess, schematic of this whole process here. Basically, we're going to have in a mine shaft, we're going to drill a shaft, I don't know, 30, 50 feet in diameter. We're going to bore it. We're going to use a tunnel boring machine. And we're going to bore like a 1,000, 2,000 foot shaft. We're going to call it the mine shaft. I'm going to introduce you to slurry mining here. Okay, the main components that I'm looking at here. All right, I have decided, I've thought both ways. I would like to have a slurry ring around our mine shaft. Okay, now I'm thinking that slurry ring should be about a half a mile radius from our mine shaft, which would give us 2 pi r circumference of just over 3 mile circumference. This slurry pipe could be made out of concrete or it could be made out of steel. In any event, it would be nice if it could be disassembled and moved to another site, okay, etc. So I'll talk more about the design of the mine shaft itself, the boring and operation of this whole thing in a minute. But you get the idea. We need this this will be at the surface. Somewhere approximately 1,000 foot higher up in depth. Let's say our test ring is at 2,000 feet. Somewhere at 1,000 feet, we will have these bladder tankers. Now they will be moored in such a way that they'll be kept at a given depth, probably 1,000 feet. Now, actually, if you pull them down, you can do different things with them. But for right now, they're going to be stationary. They will have a draw pipe that will run to a shore facility. Now, I want to tell you something here. All of these slurry feeds and return lines and stuff, you'll be dealing with a slight air pressure, but those pipes, the pipe that will be connecting the mine shaft and the ring around that mine shaft, the processing ring around that mine shaft to these bladder tankers, can be non-rigid pipes, something more akin to fire hose pipes. You know, they will have to maintain a pressure difference here from what the gas starts at to 183 bar, which is not at these depths in psi at 2,500, at 2,000 feet, you're at about 888 psi. So somewhere in that region. But the main thing here, these pipes are going to be allowing us to expand into these chambers anyway. They will be carrying slurry. Now, my idea on the surface, we'll have, I'm going to talk just a minute, because one of the surface vessels I would propose to have access to would be a directional drill, something on the surface of the ocean surface that would be a directional drill. We will be using this for a number of things. We could use it as a power source for excavation, but we'll talk about that later. The biggest thing I would really want to use this for is what I'll call pilot hole drilling for tunnel bore, for small tunnel bore machines that'll eventually be opening the shafts up more in the actual production of the slurry. However, I think a directional drill on the surface would be a big aid in helping us break open the mining. One other point to be made, on the surface, I would like to have a big solar power heater. In other words, we're just going to be pumping water. All of this will be just pumping basically even seawater. We'll just be pumping water. We'll solar heat the stuff. It'll come into the solar heat exchanger that will be below the balloons. Now this will be a closed pipe. The hydrate, the gas slurry will be flowing in this container. However, this solar heater will have a condenser in this unit that will become a heat exchanger to heat the water that's coming up out of the production ring. Okay, that will allow us to heat water using solar power to heat water that will be pumped back down into the mining process. That process, what comes up and goes down, will be closed except for the gas escaping into the contained depressurization bladder tanks. Okay, another point I want to make here about reducing the cost of mining. Okay, I want to minimize the amount of distance that if we slurry mine something, I want to minimize the distance that we're pumping that slurry, whether it's sand or clay, whatever it is. I don't want to move this stuff around. I want to move it, to process it, and then largely I want to re-inject it back into where we took it out of to help stabilize the mine that we're working in. This is going to be very good with like sand. Of course, clay is a little harder to solve, but anyway, I've got provision here. Maybe we can do some kind of tailing processing. But one of the other things, when we pump this stuff back in, I was thinking even like clay, did some kind of a hydraulic pumping or something, compressing it down or something with, we could also inject it with the CO2 and sequester CO2. To some extent, we could take denser or heavier density slurry and put it into a shaft and then kind of close it off and not process it, let it settle, and then draw the water out for later processing, different things. I'm not going to get into a lot of that. But the cost of mining here, one of the reasons I like this ring is so we can move this material around, process it, and then put it back, largely back into the area that we excavated it out of. Okay. Now, so we can generate some power and minimize the amount where we have to move this stuff. This is where this plan comes into action. Now I want to talk just a little bit about what I'm going to describe as a mine shaft. We're going to be mining, albeit slurry mining, we're going to be mining material, okay? So I'm thinking it might be a real good idea to have a mine shaft. Now this is where it gets interesting because we can use a tunnel boring machine to bore our tunnel mine shaft for us. I mean, we could do big, like 50 foot, maybe even 100 foot, okay? This is going to be just a straight vertical shaft. Now, in our test run, we probably limited to about 2,000 feet. Now, it's really funny because Elon Musk says his tunnel boring machine can bore a tunnel through granite a mile for $10 million. Now, I'm thinking we're going to do a half a mile in ice and we're going to do a vertical, so maybe we get a discount on this one. big discount. Anyway, so here you got it. So we create a mine shaft with a tunnel boring machine. Okay, this is all going to be done largely robotic. This is where your AI robotics are going to get a workout. It's all doable. I'm convinced of it. As we bore the mine shaft, I want to line it with casings. They'll probably be made out of metal, maybe probably steel. They could be aluminum. I don't know. Something that would work. They won't be necessarily that much of a structure. They'll just be a casing. But one of the things is I want to make these casings so we can remove various ones at different lengths along this mine shaft. I want to be able to take a casing out so we can put a specialized casing in its place. And most notably, as my illustration shows, a casing that's designed to allow us to hook a pipe up to it. See, in other words, that will become a little more obvious why I'm doing that later. But this will be a connection to allow us to draw material out of the hydrate region that we're mining. One of the reasons why I like the idea of putting a ring around this thing to begin with is when we start the boring machine and we start boring the tunnel, I would like to take the minings that we're getting from that boring machine and put them into this outer ring as a starting point. So we have that ring will provide us either the ability to actually wash and agitate our slurry to aid in the production, especially if we're mixing it with hot salt water coming down from our surface condenser, et cetera, et cetera. But anyway, that ring gives us a place to put working material, especially as we're initially boring this tunnel. I would like to, once we have the boring machine in place far enough in, I would like to have put the notion of putting a cap over the top of this mine shaft, a large cap over the top of this mine shaft. Now, to contain, I want what I want to call zero emissions mining, because number one, if we're leaking gas, we're leaking profits. Okay, so we want to do a zero emission mining with this. Okay, plus we can do CO2 sequestration, so we can kind of offset some of the cost of this kind of mining operation by taking CO2 from people, et cetera, et cetera. Okay, so now I was looking at a couple of options here of where exactly to hook the depressurization up, and I've thought of two different approaches. Number one, after this mine shaft is excavated, you might actually be able to do a lot of the methane processing right there in that mine shaft by pumping slurry in and out, by opening up areas, take a panel off, put a pump, a hose access panel, pumping slurry in through a region that you've bored out with a small tunnel boring machine back in. You might actually be able to produce with that mine shaft itself and not really use the ring for production. However, I like the idea of having that ring out there for production, and probably more likely having the depressurization tanks eventually hooked up to that outer ring. That'll allow us a way, perhaps, as you'll notice I have in one shot there, I show a tailing processing area where we can process tailings, where we can pump them back. Now we can also remove one of those access panels, and we can pump tailings back in to behind one of these access panels. See, so that's one of the nice things about the whole process here. But again, we have to minimize the movement of tailings because there's a lot of stuff. However, we do have adiabatic expansion of these molecules going on, which could aid, which could, if it's actually engineered properly, we could take big use, can make use of it. And I point out here where you could actually even perhaps coax what I would call a percolator, where it would, the percolator, and you'd have percolators in the ring, at least one or maybe more, where you would actually heat this water just a little bit right there at that spot, which would encourage it to drive itself up into the bladder tanks. And also note that in like clay slurry, some of the tailings may actually start to condense out on these riser pipes, which from time to time you could close and pump them down and just get a real good thick slurry, clay slurry that could be re-injected. Something I don't know. You could make clay traps. If the main thing, if you're really working with clay, finding ways of engineering clay traps would be a big help. But however you want to do it, I need to move on because I like I say, I don't really want to sit here and talk about this stuff too much anymore. Anyway, I've kind of pretty much covered a big part of it. Let me review here for a minute. Okay, welcome back. It is 06/04/2026. I'm actually still working on this CH4 report. This how you're going to use these bladder tanks in methane mining, and I've been looking at it. I've also done some of the things here I want to discuss here. Number one, some economics, just to give you an idea here. I'm gonna look at a few things. Number one, let's talk first. Go back to this idea. We're going to eliminate that solar heater. We don't need any kind of solar heater up here on the surface for anything. The reason why is after I did a little more work on this, and I realized with working with Copilot here that the release of this methane hydrate is a highly exothermic process. Okay, in other words, it generates a lot of heat all by itself. Now, this is really interesting because we should be able to generate all the power we need for the mining process from the process of mining in and of itself. I'm going to show you this here in a minute. And see, this is another thing I like to say is physics is better than magic on the surface on the surface of the ocean floor, okay? Because this adiabatic, we can actually use a gas turbine on the ocean floor without burning gas. And in fact, if we do the mining correctly, we have what we can call an engineered gusher at all times. Then we can, as you see, we can actually use an adiabatic power generator. We could put a turbine in the pipe that we're using from the top of the mine shaft to the depressurization and accumulator tanks, the bladders that will be maybe 1,000 foot up. That's where the bar change between that tube and that is gonna take place. Now it's really interesting because the actual depth at which we may be mining this, when I discuss the actual how we're going to actually mine material, I'm going to show you that we may actually be starting at a much deeper depth than that, in which case we may be producing gas at a bar rate of like 130 atmospheres. We'll be dropping that back up to 30 atmospheres, see 100 atmosphere change and stuff. Now just bear with me here. I'm going to hold on to that ring, the ring around this thing. Now that could be concrete. Part of what I'm looking at is a lot of this structure here. I don't even know if you necessarily, I'm looking at a 30-year plan per site, and I'm not actually sure that there's a reason why you would even move any of this material, any of the initial stuff that we're doing here anyway. And one of the reasons is because even after 30 years, even if we're not as actively mining, this may still be producing a lot of gas long after 30 years. I'm just going to explain the whole thing here to you. Okay. One thing is I would look at and I say, all right, so how much is all this going to cost? And I'm going to tell you, I'm actually just kind of weird. I kind of hit numbers pretty good, pretty close here. I'm going to say my mining operation, an on-site mining operation, is going to be a $5 billion investment. Okay. I'm looking at that main mine shaft and depressurization tanks being there for a long time. Now, the depressurization tanks might have to be replaced over some period of time. Who knows? But I have a rough idea of how much metal, how much casing might be, things of this nature. It's roughly about the cost of half of an aircraft carrier, very believable. And it's also about half the price of a nuclear power plant. Now, let me just kind of feed in some numbers here, okay, to kind of give you some ideas of what I'm looking at. Okay, Copilot says those bladders would be between 45 and $100 million. Now, when we're using them for depressurization of gas, I'm thinking that even that low estimate on those tanks is probably high for what we're actually going to be using them for. I will tell you though, these tanks, I've stuck at this 100,000 gallon tank size, which kind of works out real nice because it's right about 500,000 cubic feet of volume. See, so that bladder is a 500,000 cubic foot bladder. So you do about 10 of them. I don't think you're looking at $1 billion, but you might be. But if you're going to pay that much, they need to last a long time, see. The other big part here is going to be the mine shaft. And you'll note I have something that we have called the adiabatic power generator. The idea of some directional drilling and stuff going on is cool too. Let's move on into some production numbers, because what I actually start looking at, if you invest $5 billion into a project and we're looking at a 30-year return, and principally that $5 billion will be exhausted in the production of all of this. So let me just explain how I'm going to work the economics. Now, to make that just in a ballpark kind of good investment for some proven technology, I would be looking at a 30-year span where this mine would have to produce a grand total of $15 billion. Okay, a grand total of $15 billion over 30 years. Ideally, since it's a research type investment, investors would probably like to see closer to $20 billion over that 30-year period of time. Now I'm going to show you where these numbers become doable. Now, the problem is some of this is getting Copilot to go back and forth on numbers and generate numbers that I can actually believe in. But first off, let me tell you, basically I'm looking at revenues on average from day zero to the last day of 30 years, that we're going to generate $1.5 million per day in gas from this site. Now, obviously, we won't be starting out at that high of a volume, but eventually we're probably going to get to a point where we could possibly expand that. And again, beyond that 30-year period of time, there may be gas coming out of this process for much more than 30 years. The end payoff on this may be much more than this. It's very difficult. There is no commercial production of methane hydrate currently going on right now. There's some experimental stuff, some experimental ideas. Getting good numbers on this doesn't matter. I'm going to go with some of the things that Copilot told, that I worked out with Copilot, that I'm going to agree with are probably good. Number one, in order to get 1.5 million cubic feet, 1.5 million dollars in production, whatever. I had this worked out here. We actually have to fill each of these bladder. We would have 10 bladders at 500,000 cubic feet. So 10 of them is 5 million cubic feet times 3 times a day. I'm looking at 15 million cubic feet of gas a day. This is something like this is what these actually things came out to. This would be providing like $1.5 million worth of revenue. Okay. Now, so we get to this, we have to ask this big question now. How much methane hydrate, in other words, if we turn stuff into clay slurry or sand slurry, stuff like this, in terms of a physical amount of mud or clay or sand, whatever we're messing with here, how much of that do we need to process in a day to produce like $1.5 million worth of gas? And it worked out to something like 2,400 tons. Now, these figures may be totally off. It doesn't matter in the long run. I'm going to show you something here. 2,400 tons of dirt is a lot of dirt, okay? You take your average little construction dump truck, you might see some guy running out here on a construction site or something. Them things about 12 tons, some of them maybe 20 tons. So you're looking about 200 dump truck full of dirt that you're going to have to process per day to produce $1.5 million worth of methane gas, out of methane hydrate. Okay, now this is where you get into what I'm going to call a controlled collapse. I'm gonna pause just a minute here. Okay, now I'm gonna get back to this. Now this is where all the genius comes into it, because in order to make this thing profitable, we have absolutely positively got to minimize the amount of slurry or mud or sand that we move. The more we physically move anything, the more it costs us to process, to mine this stuff. Now, I'm going to introduce you into what I call an engineered honeycomb cavitation mining. Okay. Now, in essence, what we're kind of going to be doing is going to look like, we're going to look like an air bubble that just expands, gets bigger and bigger, but it's not actually going to be an air bubble at all. That's just how the material is going to move. Let me just run you by. I'm going to show you here this honeycomb cavitation mining, how this is going to work. Now, one thing is our mine shaft can be real long, half a mile deep. We can actually start with directional drilling and stuff. We can actually start one of these honeycomb cavitation points way down, even further down than that. But the idea here is I'm going to kind of illustrate here. Your first excavation here, you're just going to go in here and you're going to clear a whole bunch of sand and or clay and mud. You're going to open up an area down here and you're going to go ahead and pump that material up and put it into the ring. You're going to get it all the way out. Okay. Now, as we start moving into this cavitation mining concept, what we're going to do is we're going to go in, we're going to process slurry for a little bit, but we're going to actually work our way up and we're going to work on the ceiling. Okay. We want to actually encourage the ceiling to collapse. Okay. We'd like to make it collapse into bands if we could. Now, we could do this with some simple robotic drilling, stuff like that, a number of different things that we could do here. Okay. But the idea is we go in, we process material. To expose new material, we want to collapse the ceiling. Preferably, we'd like to control the thickness of the collapse of the ceiling. Okay. So now, as the ceiling collapses, you have a new floor that's rich in methane hydrate, and you have a ceiling above you rich in methane hydrate. So you've created this band. You've created the band between these materials of the material that's now the floor and the material that's now the ceiling. And actually, if you do this, if you engineer this right, one of the first things to realize is essentially obstacles won't matter. You know, it depending on if they're too big, you might have to go in and drill around them or open something else, another access. But essentially, as we move up, the ceiling collapses down, becomes the new floor. Okay, there's no people in here. This will all be done by robotics mining. Now, we do not want to lose any equipment. And I also don't want to put a lot of casing stuff in anywhere, because when you start putting casing in, you start raising the cost up. Now, another thing here, you'll begin to realize then, as this thing begins to expand, it starts to look like an air bubble. Okay, that's the idea here. That's why I kind of call it a honeycomb cavitation mining here. Now, the thing about it is each mine shaft can service a bunch of these. You could put these all over the place. You could actually put them a half a mile away from the mine shaft. You know, you can start them there and bring them in. So the whole idea here is these like areas here, they'll be opening up. They'll be mining so much. We'll be taking advantage of gravity and just the heat that's being generated in the mining process to break this stuff up for us, and so we can process it. We'll let the cavitation itself help release the gas. And now another thing that I found really interesting was too this idea that we got all these tires in the world, and a bunch of them. We make a bunch of them. One of the things I thought of here is if you grind tires up, if you grind them up, they're actually heavier than water. So you could actually take ground up tires from a surface tending vessel. You could feed them as down a pipe. I mean, as, you know, it could be just a regular pipe. It wouldn't have to be a high pressure pipe or anything. You could actually feed these. You'd want a direct connection to the wellhead though, or to the cap. You could actually feed ground up tires here. Could be picked up, and those ground up tires could be fed into these bands here. Like we could put a heavy band of ground up tire material in here from time to time, like as we collapse and we have a new floor. It's interesting because we can do things to backfill this material. We can use stuff like this, but one of the reasons why I want to do that at all is because it'd be nice to put some bands from time to time. It'd be nice to put a band of very highly porous material like ground up tires, because once we move on up through here, and we expose more and more material, there's still going to be gas in the material that's below it. And I'm thinking if we have a band like this, from time to time we have a real porous band of a material like ground up tires, we can actually inject heat back through them and actually continue to process material that's still in this cavitation. We just run our pipe up here. And the overall though is, in this terms of cavitation, honeycomb cavitation mining, as the ceiling collapses and becomes the floor, it exposes a large surface area of material for mining, for processing the hydrate out of. You can stir the floor up, you can stir the ceiling up, you can generate a lot of hydrate here. You break this stuff up, see. So in the overall, it as you move, each band moves up, it exposes a whole new amount of material. It's like doing the old calculus method of slicing through a three-dimensional figure, you know. But each one of these here, you get that point here where you can process it for a little, let it collapse, process it, and then you leave behind a point here where you can draw gas out of. And here, this whole idea here is why I say that as it moves on, as this field becomes mature, you may be producing gas from a given field that's been produced like this for more than 30 years to begin with. But for me, the idea of how to mine, how to actually process that amount of material to produce the required amount of gas to make a $5 billion investment worthwhile will come down to this honeycomb cavitation mining. See, it's really a pretty good idea. I'm going to go ahead and stop for a minute here. I think I'll probably do a little bit of a follow up here. I think I'm about done. I want to get back. I want to get out of this type of material, and I really want to get back into things like nation building and American history, and some of the things I've come to love more than I love math and physics. Believe it or not. When I went to school, I always thought that math and physics was everything, but I actually changed my mind over the years.